Welcome to this explainer. Okay, today we are diving into the incredibly strict, literally black and white rules that computers use to evaluate mathematical expressions. If you've ever looked at a piece of code or a spreadsheet formula and just wondered, why on earth is this behaving so completely differently than the math I learned in high school? Well, you are absolutely in the right place. We're going to break down exactly how the machine thinks and how it translates human math into its own rigid, logical arithmetic. Here is a quick roadmap of what we'll cover today. We'll start with how math meets the machine, then we'll tackle the quirks of division and modulo, cover the absolute rules of precedence, explain how assignment actually works under the hood, and finally put the whole shebang into practice.
Section 1. Math meets the machine.
Now, looking at the computer's arithmetic toolkit, you're instantly going to recognize the classics: addition, subtraction, multiplication, and division. Though, we use an asterisk and a forward slash, just standard keyboard adaptations. But a couple of these guys might stand out a bit. Since we can't easily type a tiny floating number to show an exponent on a flat screen, the machine uses the caret symbol, that little upward pointing arrow. And then there's mod, short for modulus. We're going to spend quite a bit of time on this one shortly because it represents a totally distinct operation in computer logic. To understand why we even need these specific symbols, just think about how math is usually presented to us. In a textbook, you might see a gorgeous vertical fraction, like z equals x squared plus y cubed, all sitting neatly over a 2. But the computer, it demands everything be flattened out. It processes a single, rigid, linear line of text. So that vertical fraction gets squashed into z equals, open parentheses, x caret 2 plus y caret 3, close parentheses, forward slash 2. The beautiful physical structure is completely gone, replaced entirely by a pure linear sequence of strict symbolic logic. Section 2. Division and modulo quirks. Okay, so computers are terribly and honestly sometimes frustratingly literal. There's a massive conceptual leap you have to make right here. If you divide two integers, just two whole numbers, the computer assumes you only want a whole number back. So 17 divided by 5, that evaluates strictly to 3. It doesn't round it up to 3.4, no. It literally just throws the entire fractional portion into the void. It's just gone. But check out the second example. If just one number in that operation has a decimal, say it's 17.5, the computer suddenly switches modes. 17.5 divided by 5 gives you a real answer, 3.5. Just the simple presence of a single decimal point completely changes how the machine executes the math.
This brings up a huge question. What happens to the remainder when we do that strict integer division? Well, that is exactly where our next operator steps in. The modulus operator, written out as MOD, yields only the integer remainder after one number is divided by another. And because it's purely in the business of finding remainders, the machine absolutely insists on using only whole integers for this. Both numbers simply must be integers.
It's super interesting to see how modulus plays out in the real world. 17 mod 5 equals 2, right? Because 17 divided by 5 is 3, leaving a remainder of 2. 6 mod 3 is exactly 0 since it divides perfectly evenly. But look at that very last example on the list. 5 mod 8 equals 5. This one literally trips up beginners all the time. But if you pause and think like a machine, it makes perfect sense. How many times does 8 go into 5? 0 times. And what is the remainder left over? The entirety of the 5. It's a flawless, strict application of machine logic. Section 3. The rules of precedence. So, because we completely flattened our math earlier, how on earth does the machine know what to calculate first? Well, to avoid total chaos, it relies on a strict hierarchy. This is absolute law for the computer. Parentheses rule everything. They are always evaluated first, from the innermost pair to the outermost, reading left to right. Then evaluated second is our multiplication, division, and modulus group, also processed left to right. Third in line are addition and subtraction, left to right again. But look at the very bottom of that table. The equal sign, which we call the assignment operator, is evaluated dead last. And, completely uniquely, it is evaluated from right to left.
Section 4. How assignment actually works.
Let's zoom in on how this builds into our understanding of variables. We really need to unpack that assignment operator. In human math, an equal sign is a statement of truth, right? Like, the left side perfectly balances the right. But in computer logic, it's an action. Because of that right-to-left rule we just learned, the right side of the equal sign is essentially a waiting room. The computer evaluates the entire expression over there first. It calculates the sum, divides by 4, multiplies, adds them all up following those strict precedence rules. And only after all that math collapses down into one single final result, is it passed over to the left side and safely stored in the variable named answer.
And this right-to-left behavior allows for something that looks like absolute nonsense in standard algebra. Just look at this statement, count equals count plus 1. If you showed that to a high school math teacher, they'd say it's an impossible paradox. But for the machine, it's just a basic instruction. Because it strictly evaluates right to left, it grabs the current value of the count variable, adds 1 to it, and then it takes that new result and assigns it back to the left side, safely overwriting its own original value.
Section 5. Putting it into practice. All right, here is our challenge. It's time to put these strict rules to the test and see if you've really mastered machine logic. We have variables a, b, c, and d assigned to the integers 1, 2, 3, and 4. And we're staring at this completely flattened, somewhat intimidating expression, e equals b mod d divided by c times b minus a. So, think you've got it? What is the literal first step the machine is going to take here based on our strict laws of precedence?
Let's walk through this exactly as the computer does. We start scanning the right side of the equal sign. We spot modulus, division, and multiplication. They all share the exact same precedence level, so we process them strictly left to right. Step 1, b mod d, which translates to 2 mod 4. As we learned earlier, 4 goes into 2 0 times with a remainder of 2, so result is 2. Step 2, now we take that 2 and divide it by c, which is 3. 2 divided by 3. But wait, remember the quirk. These are integers. The fraction is thrown away completely into the void, so 2 divided by 3 evaluates to a strict 0. Step 3, we take that 0 and multiply it by b, which is 2. 0 times 2 is, of course, 0. Step 4, finally, we drop down a precedence level to subtraction. 0 minus a, which is 1. 0 minus 1 gives us negative 1.
And there we have it. After flattening the equation, navigating the tricky quirks of integer division, and rigidly following the hierarchy of precedence from left to right, the entire right side of our statement collapses down to negative 1. Because the assignment operator is evaluated absolutely last, right to left, the machine finally stores that negative 1 right into the variable e. Now that you've unlocked the machine's strict mathematical language, here are a few more practice expressions straight from our source material. Actually, take a close look at number 5, where you have multiple assignment operators sitting in a single line. Knowing what you now know about precedence, integer truncation, and right-to-left evaluation, are you ready to stop thinking like a human and start calculating exactly like a machine?